Network failures happen. If you follow any amount of news, you'll regularly come across stories about how network reliability issues impact different applications. Of course, if you operate your applications on Kubernetes, you've likely had first-hand experience here as well. Developers and SREs can frequently find themselves in a blame game with the network. Your application is behaving erratically, and you don't know if it's a problem with your code or something in the underlying network. Maybe a slowly dying switch is introducing packet loss and pulling up your P95 latency. And it has a small enough blast radius that your cloud provider may never even post about it on their status page. The last thing you want to do is page half the team to debug a problem that really exists in a cloud provider. You need better visibility into your Kubernetes environment. Network monitoring today is a bit of a loaded term with a long history. It's primarily been associated with on-premise tools built for device configuration, hardware health, connectivity and capacity metrics, and occasional packet capture. As we start thinking about microservice and cloud environments, these tools really start to lose their utility. Cloud providers operate opaque software-defined networks, but they can still break and wreak havoc on an application. IP addresses and other packet-based data is often ephemeral, and it's hard to map to the actual containers you operate. And packet captures may be difficult to execute, and traffic flows may be metered and drive up cost within your cloud provider. The reality is there's a different class of use cases that emerge as we think about network telemetry in a Kubernetes environment. So what are some of these use cases that emerge? Well, first, network telemetry can give you an up-to-date, complete view of all service dependencies, so you can deploy services with confidence. If you move something or change something, you should know all the related services that could be impacted. And if someone new joins your on-call rotation, they can quickly orient themselves and understand the entire system. Second, you must be able to quickly separate network outages from application issues using service-oriented data, so you can direct troubleshooting to the right places quickly. This could mean you'll move containers off troubled cloud instances, or call in application developers with the confidence to say the network is really behaving normally. You need to end the blame game between the application and the network. Finally, you'll be able to measure and optimize your cloud networking costs. As Kubernetes services scale and communicate across availability zones, it can be difficult to connect cloud transfer costs with the actual services driving those costs. By gaining visibility into how services communicate across availability zones, you can optimize traffic patterns and reduce surprise transfer cost bills. So what do you need in order to achieve this level of visibility? The first source of information is sockets. This is similar to the flow data you're used to: source and destination IP addresses, port numbers, bytes sent, packet drops, round trip times. But it's possible to get deeper visibility into application behavior by looking at the payloads. For example, from HTTP, you can understand if it's a get or a post, the endpoint that was queried, the response code, so on. But all this really has IP addresses. To really make it useful, this data needs to be joined with information about what service is running. What's the service's version? Where is it running? The metadata that Kubernetes has becomes really critical. And actually, by stitching all this data together, now you can analyze data in a holistic way, create service maps, surface failure, and really support deep drill downs into application relevant data. Now, you could get all this data from the Linux command line. Let me show you how, but then I'm going to explain why you probably don't want to. Let's say in Kubernetes, container A wants to reach a service X, which is served by container B. Kubernetes is going to create a VIP, a virtual IP for service X. So A will open a socket and connect to X's IP address. IP tables will actually perform a NAT translation. It'll modify the packet that's addressed A to X to A to B. And B will then see the traffic as if it's coming directly from A. Now, how would we get visibility into this in the command line? Well, first from the Kube API, we can actually get information about the services and their associated IP addresses. We can next use the SS tool for socket stats. This will tell you that A is sending data to X and how many bytes actually get sent. Finally, we can actually use contract command to look at connection tracking. And we can get information about the translation from A to X and how that's translated from A to B. While it's possible to get this kind of network telemetry from the command line, it comes with some major disadvantages. Overhead is pretty high because we're running a process every time we want to get just one piece of this data. And these tools may have to iterate over every socket in the system, which can be a very expensive operation. It's also lossy since the tools might run at some regular interval and they may miss sockets that are short-lived. So we won't even be getting a complete view of the data. And finally, these CLI tools are actually limited in what the kernel exposes. They can't actually see into the kernel data structures and get the complete view of the system. This is where eBPF comes in. eBPF allows developers to run programs inside the operating system when different kernel events happen. For networking, you could run eBPF code when TCP handshake of a new connection is complete, or when TCP receives an acknowledgement for a packet. It provides an efficient way to get a stream of notifications about important events. And the BPF system call has been part of the kernel since 2014, so it's very widespread in all the major distributions. Big advantage of using eBPF for network observability is the kernel actually runs the code, so there's no changes required to the application. The kernel also contains a compiler and verifier for eBPF. So one thing this can do is actually compile to machine code, yielding a highly efficient program. The verifier will actually statically analyze the code to make sure it's free of invalid memory addresses. And for observability, eBPF can actually run in a read-only mode, so it's prevented from making changes to the underlying kernel and causing any damage. The end result is that eBPF really can give you the performance of a kernel module without any of the stability and safety issues. And it turns out to be one of the best ways of getting network visibility into your Kubernetes environment. Now at Splunk, we're big believers in the power of eBPF for network visibility. We're both contributing to this in the open source community and building it into our observability products. As one of the largest contributors of OpenTelemetry, we've donated a set of agents capable of collecting and aggregating eBPF-based network telemetry in Kubernetes environments. This is available today, and we're excited to be working with the OTel community to advance it further. We're also excited to introduce Network Explorer, a new feature of Splunk infrastructure monitoring built around this OpenTelemetry-based eBPF telemetry. Network Explorer is designed to help developers and SREs gain better visibility into their Kubernetes environments. Since it's based on eBPF, it automatically discovers service connections and requires no changes to application code or per service configuration. It can help highlight network anomalies affecting Kubernetes services, map service dependencies, and optimize communication patterns by breaking down cross-zone and egress traffic per service. Network Explorer will be available to all Splunk infrastructure monitoring customers in the next few months. Let me show you a short demonstration of how it works. The basis of this demonstration is going to be the online boutique application. It's a simple e-commerce app made up of a number of microservices. We're going to investigate some application problems that cropped up in this environment and try to determine if Network Explorer can help us understand if those were caused by a network issue. A little bit of background on the infrastructure we're using for this application. It's all running under Kubernetes. You can see the different microservices running in this environment. They're all part of the application. You can also see that we have our OTel collectors running, but in addition to that, we have our Network Explorer kernel collectors. This is the eBPF component that actually gathers network telemetry from each of the Kubernetes nodes. That data is actually sent to the centralized reducer. We usually run one reducer per cluster, and that allows it to coalesce this data into metrics that we can send to Splunk infrastructure monitoring to help us understand the network behavior of the services in this cluster. Let's jump over and actually see what this looks like in practice. Now, again, to understand the problem we're trying to investigate with Network Explorer is a set of application errors that we were told popped up, and we're trying to determine whether or not true network issues are responsible for them, or if they might be some intermittent, true application problems that our developers need to debug. And we're going to use Network Explorer to help us solve this problem. You can see there's two new navigators introduced for Network Explorer. One around network edges, one around network workloads. We're going to use the network edge navigator for the purpose of this demo. We're going to start by zooming out a bit just to make sure we capture the period where the error occurred. We're also going to zoom in to just the namespace where our important services are running. In this case, they're actually running in the staging cluster. Now, once we do that, we can actually start walking through and looking at the Network Explorer environment. One of the first things you see is the top visualization gives you a sense of overall different kinds of network errors: packet loss, round trip time, connection failures, resets. Just so you can see a current state of exactly what's going on now between your different pairs of services and how they're communicating in the environment. We're going to scroll down a bit though, so we can kind of use this to get a picture of what happened in our application. The first graph we'll look at is the TCP traffic between different services. Again, since we're looking at the edge navigator, we can actually see both the source and destination service and how traffic flowed between those two services. In this case, we can see that there was a drop between, a large one between the front end and the load generator, right around this time here, which seems like the cause of, could be indicative of where our problem occurred. If we scroll down, we can actually see some other metrics which will help us understand a little bit better about what happened around this time. One thing we'll see is network round trip time actually increased a fair bit, notably between the shipping service and the checkout service in this environment. And importantly, our network retransmissions actually spiked substantially, again, between the checkout service and the shipping service. This is really important because it tells us that some of the issues between these services were actually happening at an underlying network layer. The network was retransmitting a number of packets, so there was a lot of packet loss occurring at the time that this problem happened. And as we scroll down, we'll try to get a better picture of how this may have affected the application. But I already have a very good inclination that there was a real network problem here, and it's unlikely an application issue. As I scroll down, I'll actually see, look, there were also network timeouts that were occurring in this environment as well. And as I scroll down further, I can look at other things that are available in Network Explorer. So one is this cross-zone traffic table. Not relevant to my problem right now, but something I'll probably want to come back to because it can give me a great picture of how my services send traffic across zones, which actually affects things like network transfer costs, which I'm interested in, but right now I have to debug the problem I'm looking at. We also have graphs for UDP traffic, which, again, really interesting, not directly relevant to my immediate investigation. But what is relevant is looking here at DNS timeouts. So here I can see there were a large number and a spike in DNS timeouts right around this time as well. This is, again, correlated with the conclusion that there was a high degree of network packet loss occurring. Some of my DNS queries were actually timing out. This likely would affect, could affect my application when it happens at high enough scale. So that's an important piece of information for me to take away as well from this environment. The other thing Network Explorer can do is actually get data about HTTP. So here it also discovered that there were an elevated number of 500s responses around this time. Now, my developers knew that, which is why they asked me to investigate this as a network problem. But what I've learned is, yes, these 500s occurred, but they're not due to an application problem. They were likely due to the DNS failures and the packet loss that was happening in the network, making it unstable. And if I scroll down further, I can actually see that there was this huge spike in latency and requests as well. So we were likely seeing different timeouts that occurred because the network truly was slow. So what this gives us a picture of, by using Network Explorer, I was able to get a picture of whether the network was actually responsible for a set of problems I had, rather than problems that were occurring at an application layer. This lets me actually direct my troubleshooting very quickly to the right place and not burn cycles, trying to investigate network problems as application problems, or avoiding looking at application problems because I believe they were network problems without being able to prove it. So thanks a lot for your attention, and thanks for checking out Network Explorer.